inductive load, as example, DC motor. So the inductance is high here. Okay. Now, in this rectifier, which is full wave, as I mentioned, uncontrolled, the inductance is 0. Okay. May I ask what does this mean? If it is 0, what type of circuit we have here? Is it ideal circuit or the circuit which produce commutation? Which one?
Ideal.
Excellent. Now, if it is ideal, does this mean that the diodes, the new diode will commutate, or let me say stop the previous diode from conducting instantaneously, right? This is what I understand. It means D1, when conduct the current, will stop D3 instantaneously, no delay, directly, because there is no inductance on the supply. He told me calculate the average power supplied to the load. I need to find the voltage, the current, multiply them, the power is clear. Okay? If Vs sinusoidal voltage given to you 120 with 60 Hz. Let me ask a question here. 120, this is RMS or maximum?
Maximum.
Anybody else?
RMS.
Why? Correct, but why? Because the default. Usually when we talk about AC and he didn't tell me that this is RMS or maximum or whatever it is, average as example, we assume it is by default RMS because in AC we deal with RMS. As example, 220 volt is the a single phase voltage in Oman. He didn't tell me this is RMS or maximum, but by default I take it as RMS. Okay, then I multiply it by square root to get the maximum, right? This is what we learn. We learn Vm equals square root 2 Vs. I got the V maximum. Okay. And just I'm still explaining the question. If Vs has pulse waveform similar to this one, he gave me here pulse. It's not anymore sinusoidal. Also, he want me to find. Have a look. For this circuit, ideal circuit with no inductance, diode, no thyristor here, uncontrolled rectifier, full bridge. We know the formula is 2 square root 2 Vs over pi. We explain this in the theoretical part. Direct substitution. You get the voltage. Now you got the voltage. You are given the current. We multiply them DC to come up with the power. Easy and straightforward. Now the second situation, he gave me waveform here. Have a look at this waveform. Let me say it's close to square wave, but not square wave exactly. We have 0 here for 60 degree and then 100 degree. We have the voltage is 200. I'm reading with voice here. We have 0 and then minus 100 and so on. Okay. Now, how can I find the voltage? Integration. I mean, in the first situation, how I got the voltage in theoretical part? I integrated. For a one period, I integrated. Okay. Here, I need also to integrate. But integrate this part from 60 to 100, this plus 120, it means 180. The voltage is 200. And from this point to this point, minus 200, as you can see here. From 60 to 180, from 240 to 360, minus 200. Integrate and substitute, we directly got these numbers. Add them. 0. The average, the average, the DC average here is 0. Okay, and this is expected because they are identical. This part will cancel this part. The same voltage, 200 minus 200 here, sorry, minus 200 here, they cancel each other. It's like sinusoidal. Okay, so this is voltage is 0. If we multiply by the current, then we go 0. Now for this circuit, now let me ask a question about this circuit. This circuit contains one diode here, inductance on the supply here, so we expect commutation, right? Do we expect commutation or not? We expect, right? We expect commutation. Agree? Hello? Are you still? Yes, who's this? Are you still there? Al-Walid. He's with us. Al-Walid. Hello? Are you still with me? Khalifa?
Yes, doctor.
Great, Shamsa, great. Okay, this circuit we have inductance here, so expect commutation, right? By the way, it's worth to mention that diode D2 here, which we usually connected with the supply, with the load in parallel and in opposite direction. What we call it? We call it a free-wheeling diode. What does it mean, free-wheeling diode? It means we put it here to protect the circuit. Protect it from what? If the load have inductance and energy there, it need to release. And when it released, you remember what we say? We say the diode will be enforced to stay conducting the current in the opposite direction, which is not desirable because it's designed to conduct in one direction. So to avoid this conflict, what we do, we connect diodes similar to this in parallel with the load. So there is way to circulate the energy, rotate it, and then consume it. Now in this circuit, we discuss it. We derive the formula, if you remember, in the theoretical part. Let's see what he wants me to do. He told me that current is given to you 10 ampere. Okay. Voltage Vs 120, frequency 60, Ls. The first situation, he assumed that Ls is 0. So this means the circuit is ideal. Calculate Vd and average power. Well, definitely when I calculate Vd, I will multiply it by current to find the power. But let me focus on Vd. The second situation, he added Ls. And when he added Ls, I expect commutation. He asked me to calculate U, which is the commutation time, commutation angle or commutation time, and then output voltage, and then the power. Okay, let me take them one by one. Let me start with the ideal circuit. Now, when there is ideal circuit, it means this is half wave. It means there is no inductance here. It's half wave rectifier diode, then will conduct when there is voltage and will not conduct when there is no voltage. So directly I have the formula, I substituted. Okay. The other, then I multiply by voltage, it give me the current, it give me the voltage. Okay. 4B, when I have inductance, no. Now I have equation for the commutation. We discuss it in the theoretical part. Have a look. Omega. It's 2 pi f. Did he give me f? Yes, he gave me f 60 hertz. Ls. Did he give me Ls? Yes, 5 millihenry. ID. He gave me ID. Where is it? Just a minute in the question. 10 ampere. Vs. He gave me Vs 120. Then I substituted. I found the commutation is cosine U is 0.99. Cosine inverse will give me the angle in degree. Now, next is to find, by the way, there is no 2 here. There is no 2 here. It's supposed to be, there is no 2 here. Okay. So the voltage will be 0.45. Okay, because this is half wave. Okay. Now let's come here to Vd. Vd, we have the formula discussed in the theoretical part. Let's have a look at this, situation. This is the ideal, which we say for half wave rectifier 0.45 Vs. But there is part to be lost. You remember the half part I lost, the shaded part. Okay, you remember this part? We lose it. Why we lose it? Because of what? Anybody remember why we lose this part? Hello? Why we lose part of the voltage? Because of? Yes? Anybody?
Because the inductance.
Excellent. Because of the inductance, it makes commutation. So we make short circuit, so we lose part of the voltage. Okay. Do we have omega? Yes, we have Ls. Okay. ID. So we substitute. Have a look. The ideal voltage is supposed to be 54. But because of the inductance, we lose 3 volts. So this needs to be subtracted. This is the voltage. The voltage is lower than the ideal voltage. And when we multiply by 10, it gives me 510 watts. Now, another question here. Let me first, without reading the question, have a look at the circuit. Let me read the circuit. Okay, I have here single phase voltage. Here inductance, so this is not ideal circuit. Commutation expected, 2 legs with 4 diodes. Oh, this is fully bridge converter rectifier circuit. Capacitor, what capacitor for? Anybody remember what capacitor for? Why we connect capacitor with the load? Load here.
To smooth the current.
Current or voltage?
Voltage.
Excellent, excellent. If we want to smooth the current, what we connect?
Inductor.
Excellent, 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 excellent. Okay, he told me that the simplified circuit of single phase rectifier shown in figure with LS0 constant DC current. Oh, this is constant DC current. Sorry. Constant. It's not resistance. It's constant DC current. Okay. It means highly inductive load. Obtain the average RMS value of the current through each diode of the ratio as a ratio of ID, with ID equal ID, it means the instantaneous equal the RMS. Obtained total harmonic distortion, displacement power factor, crest factor. Okay. Now we come. Now let's have a look at diode D1 and D2. This is D1 and this is D2. We mentioned that D1 will conduct the positive part and the return will be through D2. And D3 will conduct the positive part, D4 will conduct the return of the current. Okay? So he asked me to find the current, the RMS and average current in the diodes, okay? As a ratio. I mean, this is the input, if you remember. This is the input voltage. When it comes to the output voltage, we have positive pulse and another positive pulse, another and another. So this is, let me say, full, this is full period T, which is 1 over F. Sorry, 1 over F. Now in this one, let me change the color, 1 second. Okay, in this positive pulse, D1 and D2 will conduct. In the second pulse, D3 and D4 will conduct. The next period, D1, D2, D3, D4, and so on. You got it? Okay. So when I look to the current in the diode, I will say diode current. This is the diode current. D1 and D2, only this is I, D1, D2. This is D1, D2, and then they are conducting 0 current, and then D1, D2, again, they repeat themselves. So when I integrate in one full period, 1 over 2 pi, 360, there is current in the diode D1 and D2 from 0 to pi, otherwise 0. When I integrate, it will be omega t pi, pi with pi cancelled, but 1 over 2, then ID over 2. The difference to find RMS, the same integration, but here we put square and here square root. When I do it, I got this ratio. This is first step to find average and RMS current in our diodes D1 and D2. Is it clear? Clear?
Again, Doctor.
Yes.
Again. Okay. Now have a look. He asked me to find the ratio. I mean, you have 100% ratio, okay? The total is 100%. And he asked you to see how much the percentage of the current of the total of the 100 conducted by D1 and D2 and how much by D3 and D4. So I will come to say, okay, D1 and D2, as you can see here, D1 and D2 is for one period is this part, as I say, the positive pulse only conducting. So from here, from 0 to pi, there is current. From pi to 2 pi, 0 current. So I integrated from 0 to pi, the current ID, current here, ID, okay? with respect to omega t, then it will be ID omega t. Omega t substituted by pi over pi minus 0, pi minus 0, it will be pi, and there is here 1 over 2 pi, cancel pi with pi, 1 over 2, what is left? ID over 2. Easy, straightforward. We repeat the same thing for RMS, just square here and square root. We got ID over square root 2. Now, this ratio tell me that the average current conducted by diode 1 and 2 is half the total current. And for RMS, 1 over square root 2. Now, total harmonic distortion, we back to substitute in the formula. We will find that it's ideal circuit. It's 1. For displacement power factor, again it's 1. And for power factor, I'm just substituting here. You have the formula, just substitute it. Cosine phi will be 1. Okay? Power factor, which is IS1 over IS cosine phi, will be 0.9. Crest factor, substitute them, you will find square root 2. So direct substitution. Now, these values, I will put them side. Okay? Now, let's compare the second situation when I do the same thing, but for D3 and D4. You know, D3 and D4, they started from 0 to pi, 0 current conducting, and then from pi to 2 pi, they conduct the current. I repeat the same thing. Just the only, you see here, the limits changed, okay? And the value will be minus ID, okay? They conducted the negative part of the input. So this is the percentage, and this is the percentage. I repeat the same thing. I got the same results. And this circuit tell me that when I say about power factor is 0.9, total harmonic distortion is 1, this tell me that the circuit is a good situation because less harmonics, okay? And let me say power factor is high, which is 0.9, which is good. Now, one more problem. Let me start reading the question, explain it, and then we go for the solution. A single phase full bridge diode rectifier. Just a minute. He told me single phase. This is single phase. Look how I will sketch it. Okay. Okay. Now this is diode 1, 3, 4, 2. Okay. And this is here. And this is here. Okay. But later I will sketch the load. Rectifier is used to supply DC field current to large electric machine. Just a minute, when he say DC field current, I know the field contains resistance and inductance, and this is DC motor, then it's highly inductive load. Okay, I will sketch here either inductance or resistance in series or current source. Okay, the rated field current, it means the output current, because my output is going to the field. And he told me that the rated field current is 2 ampere. This is ID. The measured resistance of the field winding is 94. He told me R load is 94 ohm. Okay. And the inductance is known to be very large, highly inductive load, you see. The bridge rectifier is initially supplied directly from 240 AC main supply. Okay, here 240 volt. Okay. Assume the rectifier diodes are ideal. Oh, he told me diode in the beginning, and here also, then right, they are diodes, are ideal. What's the meaning of ideal diode? No drop across the diode. We don't consider the drop across the diode. In real system, when we design it in the lab, we need to consider it because there is drop there, there is losses there. But here, for simplification, he assumed it's ideal. As a check, assuming the AC side inductance is 0, oh, there is no inductance, mean ideal circuit. Directly, I remember VD equal 0.9 VS. This is the formula. I remember it. Okay. Calculate the voltage which will be applied to the field winding and hence the field winding current. Okay. Let me go and I will back to the second section. Here I will say, okay, VD, as I said, 0.9 by the voltage, it gives me directly the voltage. Okay. Now, he asked me about the current. Then I have the resistance. Let me divide voltage by resistance. Ohm's law, it gives me the current. I don't know why it's not appearing here, but we divide 216 over 94. It gives me the current. Check it and find it in, find the value. Okay, let me back. Section A, done. Section B, what is the ideal power factor and displacement power factor at AC main connection? What is the expected AC main RMS? Okay, definitely ideal power factor is 1, okay? And displacement power factor, we mentioned this when we discussed it in the theoretical part, 0.9. And RMS is the same value. The same value we calculated here, similar to the DC value, it's supposed to be 2.3 ampere. Okay. Also, this has been discussed in the theoretical part. We're just copying the formula and put it here. Okay. So I finish the second part. The third part, the circuit is connected and powered. Okay. The field winding current is measured to be 2.23 ampere. Okay, this is ID. It is assumed that this voltage drop is due to the line side inductance causing commutation voltage losses. Okay, we will assume there is inductance and we will consider it. Calculate the line side inductance expressed in 50 Hz. I gave me the frequency, impedance, and inductance. Okay, I will come. The formula which we use it usually to calculate the voltage, output voltage across the load. When there is commutation, this formula, we discuss it. Okay. Now VS already there. It's constant. Omega, he gave me frequency 50. So 2 pi F is the omega. I want LS. ID, he gave me ID. In the previous section, he gave me he gave me 2.23. Okay. What is left? What is left is to find LS. VD also I have it, then I need to find LS. So I will, let me say, this taken in this side, it will be in negative, and this part taken to the other side, it will be in positive, as you can see here. This one minus VD. Okay. Now, substitute, you have everything excluding LS. You do the math, you get LS 14.3. Take care while you do the calculation, check them, you will find LS. Let me back, I did C. Next is calculate the commutation angle, U. We have formula, cosine U equal 1 minus, right? Sketch the voltage waveform, minus 2 omega L ID over square root 2 VS. Waveform which appears across the field winding, make your sketch any relative quantities. Okay, have a look. Cosine U is 1 minus 2 omega LS ID square over square root 2 VLS. We have this already calculated here. Okay, we just need to substitute. We got cosine U, then inverse, cosine inverse, it gives me the angle. Now, let me back. What he told me, make your sketch any relevant quantities. Okay, now I know that this is the sketch. It's there in the lecture notes. What I need to do, I repeat sketch it, but I will, rather than put U here, I will put U equal how much? 19.8 okay, degree. VS here maximum, so I calculate the maximum value, which is square root 2 VS. I put here value. Let me say the value is okay, you do the math. 240. Okay, it's 50 Hertz, 50 Hertz F. Okay, then the time is 1 over 50, which means 20 millisecond. You remember how we convert? Okay, this is omega t. You have time, you have omega. Find omega t for one period from here to here, and then you specify here as omega t. This degree need to convert into omega t as we learn in level 2. I explain it to you. What else? Just Let me back. He asked me about the voltage. Okay, the voltage, only the voltage. So this is the voltage. I here calculate everything, but with numbers. I sketch it, but with numbers. I will stop here because we didn't reach yet 3-phase. Inshallah, in next session we will start with 3-phase. Okay, now do you have any question?